So let's think about something about square roots that we talked about yesterday. A square root function is continuous along its domain. So if you come across a question that says, show that it's continuous from 1 to 2, as long as you can show that that is in the domain, then we know automatically it is continuous. So find the domain, you answer the question. So the domain of a square root is where x minus 1 is greater than or equal to 0. It's just where the inside is positive, because where it's positive or 0, we have defined values along the number line. So if you solve that inequality, you get x is greater than or equal to 1. And in interval notation, it is defined from 1, including 1, to infinity. And so it is continuous along its domain. So if it's continuous from 1 to infinity, then it is continuous from 1 to 2. And it's all about the fact that a square root is continuous along its domain. Okay, so that's all you have to do for a problem like that if they ask you to show that it's continuous. If it is a polynomial, find its domain. Well, it's all real numbers. Then it's continuous everywhere. If it's a square root, be careful. If it's a fractional function, it will be continuous everywhere, but where our denominator is 0, where it's undefined. So continuity, we know a lot about it. It's a lot of the functions we deal with are continuous along their domain. So if you just remember that domain and continuity kind of go together, they go hand in hand, that's all you really need for a problem like that. Okay. Now, 1, this particular square root starts at 1 and goes over. So it only kind of has continuity from the right at 1. 1 is only defined at one side, from the right side. But it's still, that interval includes 1 from the right side, so you're good. Okay. Now, here's a type of problem that you see often when it comes to continuity. And it says, find the constant c that will make g a continuous function. Now let's look at what's causing the issue with this problem. Okay, this is a polynomial. It is continuous everywhere, but it stops at 4, just before 4. This is a polynomial. It's continuous everywhere, but it stops or begins at 4, I guess you could say. So because of that, what we have to do is we have to fix the border. That's going to be our job. When I say fix the border, I mean I want the parabola and the line to match up. So I need the parabola and the line to come together. Now they're only going to come together if they're equal to the same thing. So really, I need x squared minus c squared to equal cx plus 20. And the only point that I really need for that to happen is when x is equal to 4. Just that border value. So it's actually a very simple equation. If I know I need that to be equal when x is 4, let's plug in 4. So we get 16 minus c squared has to equal 4c plus 20. So now the only thing we have to do is find c that makes that work. Okay, so how do you solve for c if it's a quadratic? Get it equal to 0. Hopefully you can factor it. If you can't factor it, you may be able to use the quadratic formula. I'm going to move the c squared to whatever side will make it positive. I think that's the easiest strategy as far as factoring it. So I'm going to add c squared. I have to subtract 16 from both sides. And now it's a factorable quantity. 2 times 2 is 4. 2 plus 2 is also 4. So that factors to be c plus 2. So we really are just looking, where would c plus 2 equal 0? So the value that would make that match is -2. Now, let me show you how you can check it. It's a pretty easy thing. So if g of x is really x squared minus 16, if x is less than 4, I just plug the c value that we just, if I plug the c value, that would be a 4. And then I plug the c value down here. And then if I said, is that a continuous function at 4? Well, you know what we would do, right? We would plug in 4. And so if you plug in 4 to this one, you get 16 minus 4, which is 12. If you plug in 4 to this one, you get -8 plus 20, which is also 12. So that is the check. And it did work. If at the border of 4, they both are going to a height of 12. So we have found the correct c value to make that work. If c is -2, it fixes the border. The only thing that you care about for most piecewise function is the border value. So the only value of x that we care about is, can we get the value of x being 4 to match? Does that make sense how we did that? Look on your face. Okay. Now, that leads us to two important theorems, the intermediate value theorem and the mean value theorem. It says, suppose that f is continuous on the closed interval from a to b, and n is a number somewhere. Now look at n. N is here. So n is here. And it is sandwiched between f of a and f of b. What the mean value theorem says is the function is continuous. So if I start at f of a and I eventually get up to f of b, there has to be at least one spot, which they called c, which crosses over and I hit the height of n. Now, that may sound weird, but what it does, this theorem allows us to pinpoint zeros for a polynomial. Now, why? A polynomial is continuous. If one value is below 0 and one value is above 0, I had to connect and cross over 0. So this, normally, the n we're most concerned about is 0 for polynomials. Where is that polynomial 0? And the intermediate value theorem does that, and it's all about continuity. If this is continuous and I start out at f of a, I had to cross over a height of n no matter what, if f of b is above it and f of a is below it. Only if the function is continuous between the a and b values. So you'll notice it's continuous. I had to cross over n. That's what it's saying. So don't make it harder than it has to be. One could be above the other, or it could be reversed. You could also go the opposite direction. That also works. Okay. So it might not make a whole lot of sense here, but it will make more sense when we apply it, I think, in the example. Hopefully. So the intermediate value theorem just allows us to find some height that we're looking for. Again, many times it's going to be a height of 0. So if a function is continuous and I start down below height I'm looking for, and above the height that I'm looking for, I had to connect. The string has to connect to that, through that height. So let's look at how that works. So it says, show that there is a root of an equation between 1 and 2. Now, a root of an equation is just where that function equals 0. Okay, so how can we show that? Well, this is continuous because it's a polynomial. Okay, so between 1 and 2, it's continuous. So let's check what is the height at 1 and what is the height at 2. Okay, what is the height at 1 and what is the height at 2? Now, if I plug in 1, I get 4 minus 6 plus 3 minus 2, and I get negative 1. Okay. If I plug in 2, I get 32 minus 24 plus 6 minus 2, which is 38 minus 26. Is that 12? Okay. Now, this is a continuous function. So this is not, there's nothing accurate about, I mean, there's a little bit accurate about this graph, but not much. Okay. This is what I know. At f of 1, I am down at negative 1. At f of 2, I am up at 12. This function is continuous. To draw from one place to another, I can never lift my finger from the pencil, or the pencil can never lift off the page. So to draw it in that section, is there any way I can avoid going through 0? No, I have to go through a height of 0. So since this was negative, and since this was positive, combined with the fact that my function is continuous, means I had to cross over 0, which is a root. So there's a root there. Now, how could you check? How could you check? Well, if we throw that function into Desmos and we check the x values between 1 and 2, somewhere it's going to cross over the x-axis. Somewhere it's going to have a root. Somewhere it's going to have a 0. So let's do that. So if I put in there 4x cubed minus 6x squared plus 3x minus 2. Okay, and let's zoom in a little bit. Is that a number between an x value between 1 and 2? Sure is, 1.221. It has a 0. It has a root. This does not help you pinpoint the exact location unless we keep getting a little bit closer together and we still find a negative and a positive, and a little bit closer together and still find a negative or a positive. There are some some calculators that's exactly how they pinpoint the zeros. They just keep truncating and getting closer and closer until they no longer have one is negative and one is positive. And you can do that. We can, instead of having the interval between 1 and 2, we can go in a little bit closer until we can try to pinpoint what that is. But yeah, as long as it's continuous, if you find one is positive and one is negative, there's a 0 in there. That's all that means. Let's talk about symmetry. And I think that's the last topic. Yes. Last topic for this section is symmetry. I've revisited symmetry in chapter 1. We did it last year in pre-calc. So I'm hoping that this does not cause you any issues. But remember, a function is even if when you plug in negative x, you get back the original function. So I always think of f of negative x becomes the original again. And that's if we are an even function. We will have y-axis symmetry, okay? An odd function, when we plug in negative x, we get the opposite of the original. So if you plug in negative x, you get the opposite of the original. Okay, that's the check you should do. Algebraically, you can check it because the if you plug in negative x, it will either go back to being the original and then it has y-axis symmetry like this one, or if it's odd, it has origin symmetry. So if you see the graph, you can check by the symmetry. If you only have an equation, you can check from the algebra. You can also put it into Desmos and see what does Desmos say the graph looks like. An even function will always have y-axis symmetry. An odd function will always have origin symmetry. So it's important that you know the symmetry and the algebraic test. So this one is an even function. It has y-axis symmetry. And here is an odd function. It has origin symmetry. This is nothing new. We've done this lots. And you can test it many ways. If you're given the graph, you can just look at it. If you're given the function, you can test it by plugging in negative x. Okay. Now, if pieces of the parts of the function change and some pieces don't, especially for a polynomial, it may not have any of these particular types of symmetry. Okay. So let's practice just figuring out if something is even, odd, or neither. Now, for a polynomial, the powers do give you a good indication, but there are ways that you can mess it up. So let's just talk about this first one. So for a here, let's plug in negative x and see what happens. So use parentheses where the original x is sitting, put in a negative x. So this is negative x to the fifth minus x, which is the opposite of our original function. And anytime if you plug in negative x and you get the exact opposite, like you multiplied through by -1 of the original, then you know it is odd. Now, you'll notice that both powers are odd. 5 is odd, 1 is odd. Okay, but if there's a constant there, if there's a +2, that's an x to the 0, which is even. Messes it up. So as soon as we add, because what does that +5 do? We know if you add something to a function, it lifts it up. It's no longer at the origin anymore. It can't have origin symmetry. So adding a number onto an odd function messes up the symmetry. Okay, let's do the next one. If you plug in negative x to this one, we get 1 minus negative x to the fourth, put it in parentheses. A negative inside of an even power is going to flip it back to a positive, so we get 1 minus a positive x to the fourth. This is the original. Oh, I'm sorry, it was G. This is the original again. Because it's the original, it's an even function. The last one, when you plug in negative x to this piece, the first piece changes sign because that 2 will be times the negative x will make it a negative 2x. But this piece, we have 2 negatives, which is going to become a positive. That third negative out front is going to keep it negative. So it's going to be negative x squared. So let's compare it back to the original. Different, that's the same. It's a mishmash. It's not even or odd. It's neither. And look at the powers. This power is odd 1. This power is even. It's a mixture of odd and even things. So it's not going to have either of those particular types of symmetry. So just use the negative x test. If you plug this one into Desmos, you can put a push pin at the origin and spin it, and it's going to look perfect. This one, you can fold it across the y-axis. This one is not going to have either of those things. So this one will have origin symmetry if you look at the picture. This one will have y-axis symmetry if you look at the picture. And this one will have no particular symmetry that we talk about. It might have a symmetry that, you know, we wouldn't necessarily care about, but it doesn't have the traditional y-axis or origin symmetry. Okay, so let's then look at the homework associated with this. So here you are going to just talk about where the function is continuous or not. Could you make this a hole right here? Because if it's not an open circle, that's not a function. So I think they just had an error. That should be an open circle. Here you're just going to sketch the graph. Here you have to check the border values. Do the borders match up, or are the borders different? Here, don't make those harder than they have to be. You're plugging in 0 and 1. If one is positive and one is negative, yes, there is a root in there. If they're both positive, it's too high. There's not a root there. If they're both negative, it's too low. There's not a root there. Or we can't be guaranteed that there's a root there. And then this is just the one, plug in negative x. Is it even or odd? Okay, so that is your 2-4 homework. Just check your date in Google Classroom for when it's due.